We've been fortunate to have him here for the past couple of years. John comes from the heart of Colorado. I'm not sure if it's actually in Buena Vista or Leadville or somewhere kind of in between, thereabouts. He did his undergraduate degree at Stanford, where he was also a student athlete, so lots of busy challenges handling both of those things. Came to us with a whole bunch of great set of skills that I think you'll see served him well in this particular project, because this involved everything from manufacturing devices and to braving incredible humidity and temperature and bugs and so forth in the streams of North Carolina, as well as then intellectually being able to decipher a tremendous amount of data and so forth. So I want to acknowledge the members of the committee. Most of you know me, Kip Solomon, chair of the committee. We have Vic Highwile and Paul Jewell as members of the committee as well. So the format today will be at least a typical one that I followed. John will give us about a 30-minute presentation on his work. Afterwards, we'll invite questions from the committee or anyone in the audience. And after those have gone for a little bit, we'll take a break, short, very, very short break, but any of you that may not want to stay for the whole defense, of course, by university policy, defenses are completely open and public, and so anyone is welcome to come back to the second part of this. My only request is if you come back to the second part, just plan to stay for the remainder of the whole defense. That second part will be a little bit more dedicated to questions from the thesis committee and that. And I think with that, we'll turn the time over to John.
Great, thank you, Kip. Thank you, everybody, for coming today. I'm going to be talking about quantification of groundwater and surface water exchange, and two devices that we developed and tested: the Shelby Tube and the Seepage Blanket. So the outline of my talk today is I'll have a quick introduction talking about the NSF project that this is a part of, and some of the difficulties with measuring mean transit times in stream bottoms, and the established methods. I'll go into the portion of my study, the methods and field area, and I'll talk about the two devices, the Shelby Tubes and the Seepage Blankets, how they're constructed, what kind of results we're getting from them, and how we're interpreting those results. So my work is part of a larger NSF project the objective is to predict nitrate loading to a North Carolina stream. This is of interest because farmers have been reducing their application for some time now, but we're not seeing a reduction in nutrient loading in the streams. So we're trying to better understand that through mean transit time, which is the residence time of the groundwater from recharge to discharge. So the other portion of this is that we're going to look at the effects of scaling on estimates of mean transit time and nutrient loading on a kilometer scale with a reach mass balance, on a 1 to 10 square meter scale with the Seepage Blankets, and in a discrete location with point measurements, which we use the Darcian method. So kind of getting more into the mean transit time, what we're trying to do is collect a representative groundwater sample that gives us all the various flow paths that are discharging in the stream. We go to the stream to collect these samples because it's a convergence zone for these groundwater flow paths, so we don't have to go poke a bunch of holes out in the aquifer and hope that we're getting the right thing with all the heterogeneity. And also the stream is a natural integrator of these groundwater flow paths, so sampling from the stream can be very instructive. So a representative groundwater sample, what that means is that we're attempting to collect a flow-weighted sample across the transect of the stream, across the perpendicular to the flow path of the stream water, and flow-weighted being that for the that the concentration is correlated with a discharge. Some of the difficulties with collecting this flow-weighted groundwater sample in streams is hyphoric flow. Hyphoric flow is the penetration of stream water into the ground and then back to the surface, as shown here in some modeling results from Gustav et al. And it makes it complicated because sampling the water that's coming directly out of the stream bottom can be this pseudo groundwater that has just recently penetrated the subsurface. So some of the established methods for measuring these representative groundwater samples. Typically the measurements are made across a transect, as I mentioned, and that's because the stream has a greater variability across the stream than it does along the length of the stream. So by sampling across a transect, we're capturing the majority of the flow paths discharging into the stream. So a couple of the parameters that we measure trying to understand this groundwater surface water interaction is specific discharge with indirect measurements such as Darcian methods, tracers, heat modeling, or an example of a direct measurement would be seepage meters. Another important parameter is hydraulic conductivity, which is most commonly measured with a falling head permeability test, and that tells you how easily the fluids can move through the sediment. And we also try to get at the chemical transport and the reactions in the subsurface by reach mass balance, measuring the loading to the stream, and also through Darcian methods, and the reactions through vertical profiles, such as the USGS mini points, which I'll talk about later. So the goals of my portion of this study as a part of the larger NSF project are to develop this intermediate scale sampling device, the Seepage Blanket, and to see if we can collect some of these flow-weighted samples. In addition to that, it was a side project, but turned into be a pretty significant part of my work is a development of the Shelby Tubes that measure specific discharge and hydraulic conductivity in the stream bed. So I evaluate these methods by comparing the results to established methods in both laboratory and a field setting. So the laboratory testing was conducted at the University of Utah and at the USGS Denver Federal Center. Here at the University of Utah, I constructed two separate devices to simulate a gaining or losing stream bottom, the seepage drum and the seepage pool. And both these devices function in the same way by routing water to the base of the container through PVC pipe and well screen, which is overlain by washed sediment or washed stream cobbles, and then that is overlain by sand or glass beads. The water is routed to the base of the container with a peristaltic pump, and the return is standing in the free water on the top. At the Denver Federal Center, the design, it's a similar seepage, a simulation of stream bottom seepage. It's just much larger, which allows us to measure multiple devices simultaneously, and also allows us to put some different types of devices into the tank that I couldn't fit into the seepage pool. The field site where we'll compare Shelby and Seepage Blanket measurements to other methods is in North Carolina, out here in the coastal plain. So it's a sandy stream bottom, and you can see West Bear Creek watershed here, and the portion that we are interested in here of West Bear Creek is blown up here in this Google image. The reach that we're interested in is a 2.7 kilometer reach here marked by the push pins. And the little section of red line here indicates the section of the stream bottom in which we did a more spatially intensive investigation with Darcian methods, Shelby tubes, and Seepage blankets. The benefits of this stream is that it's a low gradient, sandy bottom, so we can get these devices in quite easily. It's been dredged and therefore has a very regular channel, so bank storage is not a huge issue. Well, it just has a simpler stream morphology, and it's been previously researched extensively. So the field comparison for the Shelby tubes and the seepage blankets will compare Darcian methods of specific discharge and hydraulic conductivity to Shelby results. And for the blankets, we will compare seepage blanket discharge to Darcian, reach mass balance, and flow tracker measurements. And we'll compare the samples collected from the seepage blankets to piezometer samples, Darcian samples from 31 centimeters depth. Additional tests were completed during March 2013 to try and understand the effect of the blankets on high rate flow. So getting into the devices, this is a diagram of a Shelby tube here on the right, inserted into the sediment in the stream bottom to a depth of L. The important components of the Shelby tube are the tube itself, the differential pressure transducer here, and that's connected to a data logger and a readout. There are two holes that are drilled perpendicular to each other directly above the sediment surface. One is occupied with the differential pressure transducer. The other is blocked and opened with a stopper. So the data set that we are interested in from the Shelby tube is head as a function of time within the Shelby tube, and also the head in the stream. So a typical data set would look like this, with pressure on the y-axis in inches and elapsed time on the x-axis, showing that a typical way to measure with the Shelby tube. So what we do is we would start with this stopper removed from the Shelby tube and start the data logger and measure the stream head, here annotated open to the stream. And we close that, which changes the head inside the Shelby tube, and we disturb the water by removing water. For a gaining reach, we would remove water. For a losing reach, we would add water to it. But the important is we are changing the volume of the water inside the Shelby tube. We then allow that to recover undisturbed through the stream head, and then to complete the test, we again open the stopper on the other side, remeasure the head in the stream, and then stop the data logger. From this data set, we can determine the specific discharge by evaluating the slope of the recovery curve as it crosses through the stream head, as indicated by the time T sub s, multiplied by the cross-sectional area of the Shelby tube to the cross-sectional area of the amplifier standpipe, which I'll talk about briefly. In the case of an unamplified Shelby tube, big A over little a is equal to 1. For hydraulic conductivity measurements, we use the equation here. And the way that we analyze this data is we take that data set and separate it into two subsets. The zero line, which gets fit with a linear model, and the recovery line, which gets fit with a second order polynomial. We can then determine the intercept of the zero line and the recovery and evaluate that polynomial at that recovery time. Some of the issues with this analysis are that we are fitting an asymptotic curve of the recovery curve with a polynomial fit, but we get around that by taking a very small section of the recovery curve. Since we're sampling at such a high temporal resolution, we have plenty of data that we can do that. Another issue is a determination of the intercept can become difficult in cases where the slope of the recovery curve is very shallow. It becomes very sensitive to the polynomial fit. The solution becomes sensitive to the polynomial fit and where that intersection occurs. And for measurements of hydraulic conductivity, it's really important that we have a large gradient from the arbitrary time h or t sub 0 in which we measure the head h sub 0 to the head in the stream. Small differences in head create a large uncertainty associated with that. Here is a diagram of an amplifier that attaches to the top of the Shelby tube here, and you can see that it reduces the interior diameter, which makes the test go faster. It also reduces uncertainty, making the data set less noisy, and it steepens the curve as it's crossing through the stream head, which improves our analysis of that data set. So here are two sets of Shelby tube data, pressure in inches against elapsed time. And this is from the same location in West Bear Creek with an unamplified test and an amplified test. And the two things to take away from this are that the amplified test takes over unamplified test takes over 2 hours, whereas the unamplified test takes approximately 14 minutes. And the spread in the data is greatly reduced with the amplifier. So results from the lab from the Shelby tube, from the University of Utah in coarse sand, University of Utah in the fine glass beads, and the Denver Federal Center in a medium sand show that the Shelby tube is measuring specific discharge very well. The fits on these are 0.99, 0.99, and 0.94. So it's a robust measure of specific discharge. Lab results from the Shelby tube measuring hydraulic conductivity for the coarse sand, medium sand, and glass beads show that they agree reasonably well with a falling head permeability test following Genero et al. 2009. I don't have a permeability test for the medium sand, but it does fall in between the coarse sand and the glass beads, suggesting that it is measuring that pretty well. Field results from the Shelby tube. We have the amplified Shelby tube discharge here on the y-axis against the Darcian discharge, and the amplified Shelby tube hydraulic conductivity against the Darcian hydraulic conductivity. And this black line here is the 1-to-1. So you can see that there's a little bit of a scattering, but we wouldn't expect the Darcian and the Shelby tube agreements to agree on a point-by-point basis because the measurements are made in different locations, and the spatial variability is, there is significant spatial variability in the stream bottom. So while we don't see the points matching up well, we do see that the means agree reasonably well. So the mean specific discharge from the Shelby tube is 43 centimeters a day, and from the Darcian is 54 centimeters a day. And the geometric mean of the hydraulic conductivity with the outliers removed show that the Shelby tube is measuring 12 meters a day and the Darcian about 5 meters a day. So some quick conclusions for the Shelby tube. The lab and field data show that the Shelby tube is an effective measure of specific discharge and hydraulic conductivity. The method is poorly suited for low gradient measurements in which the gradient is less than 1/100th. And the use of an amplifier allows measurements to be made in areas of low specific discharge of less than 10 centimeters a day. So moving on to the seepage blankets. Here are two photos of the seepage blanket and the dilution flow meter that's associated with each of the blankets. The blankets are constructed to be low profile and a relatively flexible material made from hypalon, same material that's used for whitewater rafts. And the main features of the seepage blanket are the low profile, which I mentioned, and the metal edging here along the edges that keeps the blanket in place and also blocks off shallow hyphoreic flow up to 5 centimeters depth. And the bottom of the blanket, which I'll show in a picture later, is covered in stainless steel foil to prevent contact of groundwater with inert surfaces. The dilution flow meter shown here is attached to the port and measures discharge from the blanket by the exponential dilution of a tracer in the mixing chamber here, following the meter that was created by Shulkovets et al. In 2003 at Woods Hole. So here are a few pictures showing the blankets deployed in transect with the rectangular footprint allowing a complete coverage of the transect. Here's the bottom of the seepage blanket showing the stainless steel foil. And here's an up close of the dilution flow meter mixing chamber showing the internal perforated manifold, which helps in mixing of the tracer in the chamber and also reduces any flow past the outlets, which create apparent flow that is not measured, that would not be expected to be measured. In stagnant water, you get apparent flow. Lab results for the seepage blanket from the Denver Federal Center are displayed here in this table, with the blanket and half barrel specific discharge plotted against the tank pumping rate. Here is a picture of one of the half barrel seepage meters deployed in the field, just to give you a sense of what these half barrel meters are. The two things to take away from this data are that both the blankets and the half barrel meters are measuring less than the tank discharge. Seepage meters are inherently inefficient. The other thing to take away from this is that the blankets are slightly less efficient than the half barrels. In this case, the blanket was tested by itself, where they were designed to be deployed in a transect. So any flow path diversion is relatively easy compared to when it was deployed in a transect. And we suspect that around the corners of the blanket is where a lot of these groundwater flow paths that would be captured are being diverted around. Discharge results from West Bear Creek. Here we have mean specific discharge for March 2013 in the blue and July 2012 in the red for blankets, Darcian, reach mass balance, and flow tracker. I should mention here that the reach mass balance is conducted by injecting a conservative tracer into the stream, and the discharge is determined by the dilution of that conservative tracer as it moves downstream. So if we look at this, we can see that the Darcian and the reach mass balance results are in fairly good agreement, but the blankets in March are measuring about 160% of what the Darcian measurement is, and about 30% in July of what the Darcian measurement is, suggesting that the discharge measurements from these blankets are pretty variable. It should be noted that these mean values for the blanket discharge are well within the variation of the Darcian measurements. They varied from 1/100 of a meter per day to a meter per day. So the blankets are well within that range. So from this, the blankets are really not a good discharge measurement device. So hopefully the samples look better. take a look at that. So samples were collected from the blanket through the outlet port with copper tubing, and the first analyte that I was going to talk about is the bromide, which was injected for the reach mass balance, and it turned out to be really useful because it shows where the stream water is, because we are changing the concentration by a few orders of magnitude above background. So this plot here shows the bromide arrival at West Bear Creek, 715 meters downstream of the injection site during the March campaign. The blue line shows the stream concentration, and the red and green line show the right and center blanket across the transect at WBC 715. There are a few things to take away from this. The first is that there is clearly bromide in the blankets, suggesting that the blankets are capturing a mixture of groundwater and stream water. Well, that they are capturing some stream water. The next thing to take away from this plot is that the arrival of bromide in the blankets is slightly delayed from the arrival of bromide in the stream. The stream bromide is clearly reached a pseudo plateau, whereas the blankets have still not seen that bromide. The third thing is that the plateau bromide in the blankets is less than the stream bromide. So we're not collecting only stream water, we're getting some mixture of groundwater and stream water. We reason that this is not a leak of the blankets in which stream water is directly going into the blankets because of the slight delay, but we can't say that for sure because there is a significant reservoir of water under the blankets, and it might be that it just takes some time for that to mix and for us to sample that. So to kind of better understand whether this is a leak or not, we did some additional testing using some vertical profiles in the stream bottoms. So the main method was to use USGS mini points from Duff et al., which are displayed in the picture here, that are thin stainless steel tubes that are slotted to various depths so that you can take samples from discrete depths in the stream bottom. In addition to the mini points, we also deployed standard diffusion samplers buried in the stream bottom, and a single mini point was used to take samples from below the blanket. So look